This is a micrometer. Rotating this knob moves this shaft towards or away from this fixed point. When compared to a caliper, micrometers are configured for more specific measurement types, such as only measuring outside diameters or only inside dimensions. This is an outside micrometer, which is capable of measuring external dimensions down to 1/10 of a thousandth of an inch, or about 2.54 microns. Here I have a couple different size micrometers, which highlights the fact that most are only able to measure within 1-inch intervals. This micrometer can measure from 0 to 1 inch, 1 to 2, 2 to 3. The reason for this is because all three micrometers have the same head, which is this silver assembly. The head consists of the spindle, which is this movable steel shaft, this barrel or sleeve, which has measurements on it, the thimble, which covers up or reveals the measurements on the sleeve, and this ratchet stop, which moves the thimble at a constant force. The spindle can move at most 1 inch. If you want to measure a larger external dimension, then you have to use a frame that supports it. The frame refers to this blue C part. The last notable feature of the micrometer is this clamp, which when you tighten it, it prevents the spindle from moving and you can't rotate the thimble. If you're unable to move the thimble, then check the clamp. We will be using analog micrometers because they are more cost effective, but just as accurate as digital variants. There are a couple of cheap digital micrometers floating around online, but their quality is questionable. If you can get away with a lower accuracy measurement, then just use digital calipers. I also want to emphasize that these micrometers measure in inches. Before taking a measurement, close the micrometers with the ratchet stop to make sure that the reading is 0. If using a micrometer larger than 1 inch, then an appropriate length gauge needs to be used. For the 2-inch micrometer, you would use a 1-inch gauge, a 3-inch micrometer would use a 2-inch gauge, and so on. A micrometer is zeroed when the 0 on the thimble lines up with the middle line, which is known as the datum line. I will use this 142 thousandths of an inch gauge to demonstrate how to take a measurement. We need to back the spindle away from the fixed point, which is known as the anvil, by turning the thimble counterclockwise. In doing so, we also reveal a scale on the sleeve, where each number represents 1/10 of an inch, but we refer to these graduations as 100 thousandths of an inch. The smaller divisions are 25 thousandths of an inch each. With the micrometers open, I can place the block between the anvil and the spindle and use the ratchet stop to close the distance. The ratchet stop provides uniform pressure on the measurement piece for repeatable measurements. When it starts clicking, the correct force has been achieved and you can read the measurement. First, we look at the scale below the datum line. You only account for the divisions that you can see completely. As you get close to the next 25 thousandths of an inch, it's tempting to prematurely count that division. Do not do that. Here we have 125 thousandths of an inch. Next, we look at the markings on the thimble. This is very important. We are looking for a division that lines up perfectly or is below the datum line. We're measuring a gauge block that has a tolerance of a couple microinches. So that mark that represents 17 thousandths of an inch lines up perfectly with the datum line. Outside of measuring standards, this rarely happens. We will take a look at an alternative case in a second, but let's finish this measurement. We take our 125 thou from the interval below the datum line, and we add that 17 thou from the thimble, and we get the expected 142 thousandths of an inch. For that example, we only need to measure down to a thousandth of an inch because we used a very accurate standard. For a little bit of a messier example, where I will show you how to measure down to 1/10 of a thousandth of an inch, I'm going to use this oversized gauge pen. Before I measure the pen, I just want to draw your attention to the relationship between the thimble and this interval below the datum line. There are 25 graduations on the thimble, and every rotation of the thimble results in a new 25 thousandths mark appearing below the datum line. The thimble has to make a full rotation. So watch what happens as we get close to 0 again. See, we're jumping to that next major interval, the 100 thousandths of an inch, but we haven't returned back to 0 yet, and you can see it. So you're going to want to count this. You're going to want to say that this measurement is 400 thousandths of an inch, but it's not. We're actually below that still. We haven't gotten all the way back to 0. Now this is 400 thousandths of an inch. It just so happens that this scenario pops up with the pen, so let's go ahead and measure it. Go ahead and close. I'm going to lock the clamp just to make it a little bit easier. All right, so first thing we do is we read the scale below the datum line. And this is, you can see, as I was just talking about, in some cases, you'll be able to see another graduation, but you can't count it because if we look at our thimble, we haven't come back to 0 yet. So this would be 450 thousandths of an inch. Now we look at the thimble, and this is going to be, we look at the datum line, and even though this line right here, which would be 21, 22, is closer to the datum line, we always take the line that is at or below the line, never above it. So we would take 21, so 450 plus 21, that would give us 471. But because this line does not line up perfectly with the graduation, we're not accounting for the tenths. So we need to flip the micrometer over. And this is known as a vernier scale. If you've never seen one before, it's quite ingenious how readable it is. I'll explain that in a second. But basically, we have our tenth measurements on the left. We need to figure out which one of these horizontal lines lines up perfectly with one of the lines on the thimble. There will only be one. We kind of turn it around. Ah, bingo, 7. And one of the reasons the scale is so readable is that above the measurement, the line on the thimble will be greater, will be higher than the next number up, and then below it, it'll be beneath it. See if you can see that. So we look here on the left. You never read your measurement off the thimble for the tenths. We look here on the left, and it is 7. So our measurement will be 471 thousandths of an inch and 7/10ths of an inch, or 0.4717 inches. If you're new to micrometers, you might want another example to reinforce what we just went over. I'm going to do another measurement, but I'm going to use a different caliper. We're going to use this one. Now the main difference between these two calipers is the geometry of the anvil. Flat versus round, some curvature here. Now these calipers are meant to be used to measure the wall thickness of pipes. I hope you can understand why you'd want kind of a round anvil versus a flat one for this measurement. These two calipers have the same heads, so the measurement technique is the exact same. We'll put the tube between the spindle and the anvil. This is actually how I hold the micrometers so that I can hold the workpiece steady and keep it perpendicular. But that's not very amenable for videoing, so I'm just going to turn it to the side. I'll go ahead and lock them. Now, we haven't hit the 0 again, so we can't count that last graduation that's still kind of stuck underneath the thimble. So that would be 50 thousandths of an inch. Now we need a mark on the thimble that is at or below the datum line, so that would give us 21, 22 would satisfy that. So 22 plus 50, 72 thousandths of an inch. Now that 22 is not at that datum line, so we need to pick up those thousandths of an inch, flip over to the vernier scale, and we're looking for which one of these horizontal lines lines up with one of the intervals on the thimble. And to me, that looks like 5. Remember, we discard these measurements when trying to determine how many tenths. So it would be 0.0725 inches, 72 thousandths and 5/10 inches. And with that, we're able to pick up outside dimensions and diameters with the external micrometers. We can use the special wall thickness micrometers to pick up the wall thickness. But what if we wanted to know the internal diameter, the ID of this tube? Well, we could probably buy a set of internal micrometers. And yes, those do exist, but they're expensive. And again, they only work for certain ranges. So I have to buy a bunch of different ones in order to cover the full gambit. A cheaper option is to pair external micrometers with telescoping gauges. We're going to cover how to use these in the next video.